Hello, today I'll be going over how to draw in the resonance structure for organic chemicals. Now the first thing I suggest everyone do is to draw in any of the lone pairs that you see. So for instance, on this oxygen, there would be 2 lone pairs. And then another lone pair on this carbon at the end with the negative charge. So before we get into anything, the number one thing to note is the charge on the overall molecule. So this overall charge on this molecule is -1. And so this will be very helpful when we continue our resonance structures. So we're looking at, the first thing I suggest is to look at the non-carbon atoms. Usually these atoms will be the one with the lone pairs that are available for either being put into making a pi bond or into accepting the electrons from a pi bond. So here's an example. You see this pi bond here? It can take the electrons, but at the same time, this would make this carbon here a carbocation. And remember, carbon has the octet rule. And so when we move this, we should also negate it with something, right? And so look, we have a negative charge here and a lone pair. So what if we were just to put it into making a pi bond? That would give us an oxygen with 3 lone pairs now, which would make it have a negative charge. And we're putting the electrons into this pi bond, which would not only fulfill the octet rule here, but it would also take away the negative charge here. And do you remember what I said earlier? The overall charge of the molecule must always be the same. So yes, we still have the negative charge here, but that is actually what we want. We want the overall charge of the molecule to still be the same. So I've just drew another organic molecule that we can take a look at. And so here we have a carbocation, but there's no lone pairs to fill in. So what do we do in this case? Well, there's still a charge. And so if there's a positive charge, kind of like what we did here, we knew that the electrons were going away, which would create a carbocation, create a here. And so in order to negate this positive charge, we would try to fill it in with something negative. So basically the rules that you should remember are moving lone pairs and also negating the positive ones that you do have. And so before we get into anything, there is one thing that we can do already. Look here, we have a benzene ring. A benzene ring means that we can move all of these pi bonds just one over, because benzene rings do have the resonance structure where you can move these pi bonds. And if you notice, they're still all the same. For instance, this carbon has 1, 2, 3 plus a hydrogen. 1, 2, 3 plus a hydrogen. Still the same. This one has 1, 2, 3, 4. 1, 2, 3, 4. It's only that the positions of where the pi bond was originally has just shifted, but it's still completely the same. Okay, now that we have that out of the way, let's take a look at this carbocation. We need to negate it somehow. Where are electrons available for that? Well, look here. We have a pi bond right here that we can take. And so let's just make this a little easier. I'll use a different color. This one I will skip a couple steps. We take the electrons from this pi bond, we put it into this carbon. But now this carbon will be negative. And carbons don't like to be positive or negative if it doesn't have to be. So what if we just put it into a pi bond? And right here, with the pi bond, not only will it relieve this carbon off of its negative charge, but it will also, remember when we put it here, it's going to turn into a lone pair. It's also going to relieve and negate this carbocation. So let's do that. We're moving this here. So now there's pi bond here. The carbocation is being neutralized. But remember what I said? The overall charge must always be the same. So overall charge positive 1, overall charge positive 1. Where is the positive charge on this molecule? Well, we took the pi bond from here. This one still has 1, 2, 3, 4, 1, 2, 3, 4. So it must be this one. It's missing a bond. Or not missing a bond, but it's missing some electrons. So this would be positive. Let's see. Remember, we're trying to negate positive charges as much as possible before we run out of resonance structures. What if we just move this pi bond here? Remember, I'm skipping over steps a little bit. Technically, what would happen is we take this pi bond, we put it in as a lone pair on this carbon, and then we take this lone pair and then we put it in a pi bond. But I am skipping a couple of steps. Okay, let's see how that would look like. Okay, we're putting the pi bond here. So it's negating this positive charge. And so now where's the positive charge? Well, the positive charge must be here. It's missing. Okay. How else can we do? If we move this one back, it's going to be exactly like this molecule here. Let's move this pi bond. Okay. Move it onto this carbon as a lone pair. Then this lone pair will jump in as a pi bond. And remember, these are resonance structures, so the arrow goes both ways. I'm sorry about that. Okay, move here. Okay, now where's the positive charge? Move to here. This one is missing it. Let's see. Is there anything else we can do? We can't move it back because it would make the same structure. And if we move it back here, we would make the same structure here. So I think we are done with all the resonance structures for this molecule. All right, I do have one last molecule for us to practice with today. And kind of going back to the first example, number one thing you should do is fill in those lone pairs. Okay? And let's kind of get started. Let's first move this pi bond here, kind of like what we did last time. And if you'll notice, when we move this, now this carbon will be missing a bond. And so it will so the intermediate structure will kind of have a carbocation. But look, we have another lone pair here we can use. Let's move it here. Okay. Have a negative charge on the oxygen. Now the nitrogen will be positive because we are stealing its lone pair that it usually likes to possess for itself. But now we don't have a carbocation intermediate. We try to avoid that as much as possible, hence why I'm not really leaving it as its own resonance structure. Alright. Looking at it, are there any resonance structures that we can do for this one? I don't think so. You may be thinking, oh, well, this is a ring. But if you notice, if we hypothetically move this pi bond here, it's going to be violating the octet rule. What if we move it here? Well, it'll still be violating the octet rule. There's no place we can move it without violating the octet rule. So we'll leave it there. I guess since we're here, we should put the double-sided arrow. I can just write the intermediate structure. Basically, this would look like this. Yeah, and so let's look at the overall charge. The overall charge of this molecule is neutral. And the overall charge of this molecule is neutral because the positive cancels out the negative, and so do we have for this one. I would say this one would be more of like an intermediate structure just because we don't see a lot of this, but this is also an option. All right, thank you so much for joining me, and please let me know if you wish to see more videos like this.